let me share the screen now. Can you see the full screen?
Yeah.
Yes, so thank you very much for this great opportunity to participate in this very nice seminar series. So I will actually be talking about slightly broader about direct dark matter detection and of course the dark photons. So here's a very nice slide from 2008 that I'm sure many people are aware. There's many dark matter possibilities. And let me briefly start with some general comments about direct dark matter detection. So in direct dark matter detection, you detect the energy deposited within the experiments from the Milky Way halo dark matter passing through the Earth. And the conventional direct detection searches, they focus on nuclear recoils due to electroweak scale WIMPs within large, and here this means ton scale experiments, and looking for the signals that way. Now, as we all know, there have been many great efforts, but there's no convincing science of dark matter, so the strategy is to probe farther with new, larger experiments. And of course, with the xenon 1 ton, any kind of new anomalies will keep the theorists on the edge and looking forward to any new discoveries. So as you probe deeper with these large experiments, the conventional direct detection WIMP searches, you will eventually encounter the so-called irreducible neutrino background, the neutrino floor. And this is so some plots from the work with Graciela Galmini and Sam Witt about the general studies of neutrino floor. And on the left-hand side, this is in the snow lobe location. You can see all these neutrino fluxes, the solar, atmospheric, and other fluxes. And the point is that they start to mimic, they will mimic WIMP signal. And so this will reduce your ability to discern the dark matter detection versus something else. And the right-hand side is just an example of what is the problem, that these different curves show different exposure. As you probe down exposure, you can see that there's a little blip there, right here, and this just means that you're degenerate with the background. In this case, it is the solar boron 8 for a 6 GeV WIMP. And so increasing the exposure, meaning the size of the experiment, you do not gain much sensitivity. So this is a problem. And so all of this is a curse for dark matter, but this can be thought of as an opportunity for neutrino physics. And hence I would like to advocate the view of thinking about these large experiments, even if they're not so good for WIMPs later on as they become very big because of this problem. They are great effective neutrino telescopes, and because of low thresholds and enhanced coherent scattering, you can do very interesting things that are complementary to regular neutrino observatories. In particular, you can say some interesting things about pre-supernova neutrinos, as we did in this work with Nirmal and Sam, geoneutrinos, to see what happens inside the Earth, and a lot of other things. So this is the general comments about so-called conventional large-scale direct dark matter detection. Now, the dark matter parameter space is, of course, very vast, and this is a very nice summary slide from US Cosmic Frontier Report from 2017 to give the summary of the field. I mean, of course, there are some changes here. So this shows the scale of interest in terms of mass, the various dark matter candidates, some anomalies, and there's some new ones, the various search techniques. And as you can see, the conventional direct detection WIMPs only focused in this very small region, which is, of course, very limited. And a very interesting region where the dark photons will be is right here, the ultralight dark matter region, which will be the next commentary. But the basic point from all this is that without convincing science and with very large theory and uncertainty, it is important to search broadly. And as you can also hear, before I move on to the photons, let me also mention that there's a very interesting thing here. Black holes, the primordial black holes, and actually about 2-3 weeks ago, together with other people, we put out some very interesting new, totally novel limits in the LIGO range for PBH. So please check this out. Now, going to the dark photons, let me tell you about some new opportunities. So dark, or also known as hidden photons, just a brief summary. So these are the vector bosons of additional dark sector U1 local symmetry. They can appear in minimal extensions with a standard model, and they're also well motivated from top-down constructions. In particular, in various compactifications, if you are interested in more like stream motivated constructions, they often appear many U1s. So take that as you will. Kinetically mixes with a standard model photon. I'll come back briefly to this later. The mass can be obtained either from the Stuckelberg or the Higgs mechanism. And if the mass of the dark or the hidden photon that you consider small, it behaves like a coherent classical field on some scale. Now, the abundance, the present day abundance is set by the early universe formation. And so the most popular mechanism for these types of things, including or the ultralight bosons in general, is the misalignment mechanism, where you have the initial angle offset. Then there's also inflationary fluctuations, and there's decays of various precursor fields that can decay to this particle. But there's a lot of model uncertainty, right? But the basic point is it depends on the model. And also, since this is a vector field, it can have a direction. And here again, you have some possibilities. The direction is either aligned or not aligned. And this again depends on the model. So there's many different possibilities and combinations of these things. And they were basically all effectively model dependent statements. So for the purposes of the plasma haloscope, I will consider a more phenomenological approach where I don't deal with all these issues and just consider it some parameter space. And of course, as I'm sure the experts in the audience know this very well, with the xenon one-ton excess, several groups have pointed out that dark matter, dark photon can fit the excess within a certain parameter space. Okay, so this is a general brief overview. So what is the status of the dark photon? So here is a relatively updated plot compiled by the Funk collaboration of the hidden photon mass versus the mixing parameter on the y-axis and the masses on the x-axis. And so there's various different regimes of interest. So the various haloscopes and the regime that I will be describing next lie right here in the allowed dark matter regime. There's some cosmological bounds right here, and then there's also the bounds from the astrophysics, the solar lifetime, horizontal branch stars, and so on. But this is basically the status. And right here is where you can fit the xenon one-ton excess. Okay. let me briefly mention about conventional haloscopes, as this will be the main benchmark for the parameter space of interest. So the conventional, so to speak, cavity haloscopes, first introduced by Sikivi, but of course very many other works and improvements later on. Their main purpose is to search for photons from axion conversion, but they also are well equipped to search for dark photons. And here is a schematic of one of the leading experiments, the ADMX. So the axion comes in within there's a B field within a resonant cavity. So you then produce a photon, and to maximize the signal, the photon frequency should be matched with the resonant frequency of the cavity. Okay, and then you can read out the output. This is the basic scheme, and of course, this is a very oversimplified picture, but that is the basic idea. Now for the dark photon, it is basically very similar to this, but you do not need the B field, as you can see in this picture for the axions. Now, for this setup, for these cavity haloscopes, as I mentioned, the conversion is enhanced at the cavity resonance mode. So, but this is limited, of course, by the cavity geometry. So the parameter space that you can probe with these experiments is somewhat limited. For example, you cannot make the cavity infinitely small, of course, and so on. Now, of course, there are other proposals that include dish antennas as well as dielectric haloscopes such as MadMax, and these also exist. Okay. Let me now briefly mention about in-medium effects. So many proposals to detect light dark matter, and here I'm talking about a bit more generally about light dark matter, such as those based on superconductors and so on. There can be summarized, and again, there's many individual details and so on, and technicalities, but they can be summarized as based on small gap material, and above this gap, there's an efficient quasi-particle production. And here this means photons, or in the case of the spin wave, the magnons and so on, but this is basically the general summary. Now, near the quasi-particle production resonance, in-medium effects will suppress the interaction. So that is not good for your signal detection, obviously. However, if somehow you manage to stay on the resonance, that means that you will dramatically enhance the interaction rate. Okay, and this is where the tunable plasma haloscope comes in. So the tunable plasma haloscope has been recently introduced in this work by Lawson et al. With Frank Wilczek, Edoardo Italiano, Alex Miller, as well as I think there might be some other authors. And it utilizes axion-plasmon coupling compared to just the axion photon coupling, as in the case of the cavity resonator. And the basic structure of this haloscope is based on wire metamaterials. So metamaterials is a novel class of materials that is quite popular in condensed matter, and this word encompasses actually a very large class of materials, but basically this means that there is a general small randomized or not randomized structure in such a way that it gives material totally novel properties. In this particular case, these are wire metamaterials, and this was introduced in a seminal paper by Pendry. And the point here is that the structure of thin wires, so you imagine some configuration of thin wires, they behave like a metal. So you arrange a bunch of thin wires and they behave like a metal. And the interesting property here is that as you change the spacing of these wires, you effectively change the property of this wire metal that you have, including such things as the plasma frequency. Okay. And what happens here is the axion couples to the plasmon within this wire metal, so effectively to the plasmon within this effective metal. And since you can change the position of wires, you can also, that means, tune the frequency, in this case the plasma frequency, in such a way that you're always on the resonance. And what this means, going back to my previous comments about in-medium effects, is that you take advantage of the in-medium effects rather than having them as a hindrance, as in a lot of proposals they are. Additionally, the resonance frequency is not limited here by the geometry as it is in the more conventional cavity haloscopes, where the frequency is set again by the cavity resonance mode. Okay. So this is kind of a best of both worlds in terms of geometry, in terms of these in-medium effects. Right. And here's a schematic from Alex Miller that you have this cylinder. You envision this cylinder, basically it has a bunch of wires. The wires are aligned. And here's a coherent wave coming in and interacting with them. Okay. Now, in this recent work with Graciela, Alex Miller, and Edoardo Italiano, we pointed out that these tunable plasma haloscopes that have been proposed are also very good for dark photon searches. Right. And here, similar to the case of axion, you have the dark photon plasmon interaction. I would like to note that while dark photon plasma interaction has not been considered in laboratory settings before our study, this has been pretty well known in case of astrophysical environments. There's many important works by Geir Grafeld, Redondo, Maxim Pospelov had works on this also, and so on. And this is a laboratory application. And here, just give some general comments. You have a kinetic mixing of the dark photon X with the standard model photon, right? So you have the two kinetic terms. You have the mixing term, and you have the mass term and the coupling to the current. And since you're now in a medium, that means you need to introduce an additional piece to characterize the medium, and this is done by inclusion of the polarization tensor. Okay, like this. Now, if your medium is, your medium can be isotropic or anisotropic. In the case of tunable plasmascopes, since the wires are aligned or envisioned to be aligned in a particular direction, the medium is highly anisotropic. And so this has some ramifications about basically what is happening with this polarization tensor. But this is the general setup. And then the properties of the metal, which I was mentioning before, they're encoded within the how the polarization tensor is related to the dielectric tensor. Okay. So now you have this Lagrangian with this additional piece. And so you can describe then your whole system based on modified Maxwell equations. Namely, starting with this Lagrangian, you go and you work out the wave equations and describe the system in terms of the E and B fields. You find the produced electric field in the medium, and then from here on, you can then discuss what is the response. Okay. So this is a macroscopic description, but then of course you can go to the microscopic particle physics description and match the macroscopic description. So in the microscopic description, this is most well done in terms of thermal field theory language. And here, the basic point is one uses optical theorem to relate the dark photon absorption with the dark photon self-energy. So this is the general strategy of the thermal field theory, and the dark photon self-energy already contains the in-medium effects, okay? And so the results that you obtain from this then can be matched to the results that you obtain from macroscopic Maxwell equations. All right. Then you can finally, after you have worked out your system description, you can ask what is the resulting output power from these interactions. And here is the result presented in terms of quantity, presented in a way that is similar to the conventional haloscopes. And here the chi is the kinetic mixing, Q is a quality factor. This is basically the size of the detector, approximately meter square. Dark matter abundance, a geometric factor of order 1, the signal efficiency, and the frequency that you measure. Having obtained the power, you can then, you have to read out the power, so then you can relate the output power from this interaction to the readout signal to noise ratio through the, for example, the decays radiometer, which is also a standard way of doing things for the cavity haloscopes. And here you have the signal to noise is related to power versus the temperature of the system, which is basically the noise temperature. And obviously this is, the result is then very sensitive to to what you plug in for the noise. And here you also then have the scanning time, delta t, versus the width of the signal. Okay, so this is the system description. Now, as I mentioned before, you do not need for the dark photon studies the B field like you do for the case of X-ions. So what this means is that your detector design is less restrictive, because if you're considering a 1 meter square detector and you need a B field, then I mean, this needs to obviously take into considerations because there is also cooling and so on. So all these things need to be combined. But once you do not need a B field throughout the volume that you consider, this obviously is significantly less restrictive. And so, in fact, the parameter space that you can probe that we showed could in principle be quite sizably bigger for dark photons with these tunable plasma haloscopes than originally proposed for the X-ions. So this is very nice, and this is a very good application of these proposals. And here, what is shown here on the, again, on the y-axis is the kinetic mixing, on the x-axis is the mass of the dark photon. The ADMX and haystack are the current limits from haloscopes. MadMax is the dielectric proposal shown here for reference. And the dotted line versus the straight line denote how results will look different depending on the noise temperature that you plug in. So the bigger straight line without the dashes denotes that your noise is quantum limited. And this is obviously a very optimistic scenario. But the fact that you can cover this very broad range is very promising and encouraging. Okay. Let me discuss one more thing about the dark photon, is that you will also have signal modulation. So let me just remind you that you're moving in the galaxy, and the Earth is also experiences motion as well as rotation. Now, because of this, because of the Earth's motion with respect to the galaxy, you will have a signal annual modulation as well as very small daily modulation. Now, on top of this, as I mentioned, there is a lot of model dependency, but in some models, the dark photon, dark matter is actually clumped. And if you have clumps, then this will, in addition to this modulation, to this expected modulation, you will also have erratic modulation due to these clumps. Additionally, since this is a vector field, and as I mentioned, depending on the model, it could be either aligned or randomized. But since you have a highly anisotropic detector, your signal depends on basically the dot product of the direction for the detector versus direction of the field. And the Earth's rotation will then induce a modulation. And this is another distinction with the axions, because in the axions, they do not have this. Since you do not have this, it's not a vector field. Now, what is the point of all of this discussion? Well, the point is that this modulation is actually one of the key components to confirming that an observed signal is dark matter. Because just as you observe signal, the obvious question is, well, does it come from somewhere else? And observing such modulation will be an important confirmation. Additionally, you could also shed light on the dark photon production mechanism, since some mechanisms, they prefer modulation, they prefer alignment of the field or not. Okay. So that's what I want to say about dark photons, and now let me briefly mention about scalars, piggybacking on the related topic of the in-medium effects. So in this work with Graciela and Eduardo, also from several weeks ago, from a separate study from dark photons, we pointed out that the scalar medium effects, analogous to what I just described with dark photon, are also relevant. And again, scalars are the simplest extension of a standard model. And if you're interested in scenarios coming from top-down constructions, you expect very many moduli, scalars, and whatnot. And so everyone loves scalars, and they can also contribute to dark matter. And while it has been previously neglected in all the proposals, in identical analogy to what I just mentioned for the dark photon, scalars can also mix with plasmons and experience in medium effects. And again, as I mentioned before, this could strongly affect the detection rates. So the scalar and medium effects have been noted for astrophysical sources in Hardy and Lesson by paper in 2016. And this is the first mention of them in the laboratory, in the conventional laboratories. Right. So the bottom line is, in a lot of proposals that people have considered, the light scale dark matter detection could be significantly affected. And just to show you how this could be, so this is from semiconductors, from the paper by Hodgeberg, Tong-Yan Lin, and Catherine Zurich. This is the sensitivity from the paper, the old sensitivity, and this is if you multiply by the suppression from these in medium effects. Now, of course, a more detailed study of all this needs to be done to see exactly how the suppression is and how it is affected in various proposals. But with this suppression, it could be very significant. In this particular case, it appears to be so. In fact, many orders. So this appears to be an important consideration. Now, what are some ways how you can mitigate these effects? Well, first is you stay far away from the resonance. So then you just do not have to deal with them. And while dark matter is moving very slowly, you can, if it's moving very fast, then you will be far away from resonance. And this is the case of boosted dark matter. And again, people have revisited the boosted dark matter from, in the case for the xenon wantan. And I know there's some experts in the audience who actually wrote some very nice papers about related to the excess. So another possibility is you can exploit the resonance itself, namely that you stay in the resonance. And this is the case with the tunable plasma haloscope. So again, assuming there are such effects, this highlights a particular set of proposals as very promising, and tunable plasma haloscope seems to be one of them. Another is Dirac materials, which if you have a small enough gap, then you can also gain similar sensitivity. But that basically means that you're becoming closer and closer to resonance. All right, so let me now summarize. So there are many new ideas for direct dark matter detection, but since there is no established observation and there's very significant theory uncertainty, it is very important to search parameter space broadly. Now, as I have tried to briefly advocate, large dark matter experiments, even if they do not discover WIMPs, they are great for neutrino physics and can provide complementary results to the upcoming large experiments such as Hyper-K, Dune, and so on in certain ranges. So that's, of course, very nice. Now, light bosonic dark matter, going now to light bosonic dark matter, this is very well motivated. And the newly proposed tunable plasma haloscopes address the limitations of some of the previous proposals, in particular limitation regarding the geometry of the experiment, and also exploit these in medium effects. And they appear to be excellent dark photon detectors. And in fact, with more sensitivity than for the X searches. And finally, in the case of scalars, the medium effects have been previously neglected, but if these effects are there, they can very significantly impact the experimental rates. And again, this highlights some particular proposals, such as Dirac materials or tunable plasma haloscopes, as particularly efficient. Thank you very much for your time.
Thank you very much for your interesting talk. So, are there any questions?
Yeah. So may I ask, like, how do you really assemble these wires, like in your system, and where does the signal come out, and how do you read it out?
Yeah. So I don't have too particularly much to say about all the technical designs. Most of the technical designs are basically very similar to the original proposal by Alex Miller, Bilchek, and others. So I don't have too much to add to this. I mean, you're basically asking how do you build this, right? So
yeah, how does the photon come out? Like you talk about like the signal power, like but yeah, you need to read it out.
Yeah, you need to read it out. So for readout, that's why I put the decay radiometer formula. So this is basically a radiometer readout, and I don't have. So this is as it was done in the original proposal, and I don't have anything to add to that.
Do you need to do focusing in this case? And like, how many of these receivers do you need?
How many? Sorry, how many
receivers do you need?
Oh, I don't have any particular comments on the very detailed technical design.
Okay.
And let me just briefly mention before going to other questions that as with all other proposals, as with all other proposals, until this is fully built, I think that some design elements are in flux. And that is, by the way, it seems to be actually the issue with a lot of these things, that people are just on the plot, they put some arbitrary line where they just have some sensitivity, whatever they want. But I mean, until this is built, you know, a lot of these design elements are somewhat in flux. But I don't have anything to add to the original proposal in terms of technical limitations. So.
Any more questions? I have a question. So are you also? I take it you are also working with some instrument builders. So this will this be built somewhere, or is it considered to be built?
Sorry.
Is this kind of? I mean, are you also working together with some instrument builders? Is this proposal being considered for actually building this detector?
You mean the tunable haloscope?
Yes, yes.
So I personally do not work with the Enzo Miller, but Alex Miller does. And as I understand, there is to my understanding, there is a group in Berkeley, experimental group in Berkeley, who is working on considering these things. And additionally, as I understand, in Stockholm, there is also a group who's seriously considering it. So to my understanding, the answer is yes, but I don't have more comments.
All right, thanks. So I think it's time to move on to our next talk. Thank you again, Volodymyr. So our next speaker is Fengwei Yang.